we stand on the brink of a new era in robotics. For decades, robots have populated our factories, performing tasks deemed too dangerous or repetitive for humans. But these machines, often large and cumbersome, are confined to controlled environments. Now imagine a world where robots, small as insects, could navigate the complexities of our world. This is the vision driving the brilliant minds at MIT. They are pushing the boundaries of what's possible, creating robots so small they can perch on a fingertip. These aren't mere toys. They are sophisticated machines with the potential to revolutionize fields from agriculture to healthcare. What makes these robot insects so compelling is their potential to go where no robot has gone before. Imagine a swarm of these tiny machines, deployed after a natural disaster, navigating rubble to locate survivors. Or picture them in agriculture, pollinating crops with precision and efficiency. The possibilities seem endless. The development of these robots is no simple feat. It requires a deep understanding of biology, material science, and engineering. MIT researchers are drawing inspiration from the natural world, studying the flight of insects and replicating their intricate movements in their creations. The journey towards creating truly autonomous, insect-sized robots is still ongoing. However, the progress made by MIT's researchers is nothing short of remarkable. This is a testament to human ingenuity, our relentless pursuit of knowledge, and our desire to create a better future. The future of robotics is small, and it is buzzing with potential. Subscribe, like, and share Cosmo Academia. Building robots the size of insects presents unique challenges. One of the biggest hurdles is surface tension. We rarely think about it, but water molecules have a strong attraction to each other. This creates a force called surface tension, which acts like a thin skin on the water surface. For tiny creatures like insects, surface tension is a significant force to overcome.
Imagine a fly landing on a pond. The surface tension of the water tries to prevent the fly's legs from breaking through. To overcome this, the fly has to generate enough force to push through the water's surface. For small flying robots, this is a major challenge.
Traditional aircraft wings generate lift by creating differences in air pressure. However, for insect-sized wings, the viscosity of air becomes a dominant factor. The air feels much thicker and stickier at this scale, making it harder to generate lift. MIT researchers are tackling these challenges head-on. They are developing new materials and designs that mimic the hydrophobic properties of insect wings, allowing their robots to repel water and navigate environments with high humidity. They are also exploring alternative wing designs and flapping mechanisms that are more efficient at this small scale. Nature, the ultimate innovator, has already solved the problem of flying at the insect scale. Bees, with their seemingly effortless flight, have fascinated scientists for centuries. Understanding how bees fly has been crucial to MIT's work on robot insects.
Unlike airplanes, which rely on fixed wings and aerodynamics, bees flap their wings in a complex figure-8 pattern. This motion creates tiny whirlwinds of air, called vortices, which generate lift. The rapid flapping and rotation of their wings allow bees to hover, maneuver in tight spaces, and even fly backward.
MIT researchers have studied bee flight extensively, using high-speed cameras and computer simulations to analyze their wing movements. They have incorporated this knowledge into their robot insect designs, creating artificial wings that mimic the flapping patterns of their natural counterparts. By studying the subtle intricacies of bee flight, MIT researchers are unlocking the secrets to creating agile and maneuverable miniature flying robots. This bio-inspired approach is pushing the boundaries of robotics and paving the way for a new generation of flying machines. Building tiny robots is one challenge. Powering them is another altogether. Traditional motors and batteries are simply too bulky and heavy for insect-sized robots. To overcome this, MIT researchers have turned to artificial muscles.
These artificial muscles, made from advanced materials like piezoelectric ceramics, contract and expand in response to electrical signals. They can generate a surprising amount of force for their size and are far more efficient than traditional motors. This efficiency is crucial for extending the limited flight time of these tiny robots.
The development of these artificial muscles has been a game-changer in the field of robotics, particularly for microbots. These muscles allow for more lifelike movements and greater control, enabling the robots to perform delicate tasks that would be impossible with conventional motors.
Section 5. Jumping on Mars Pogo Stick Locomotion. The quest for miniaturization extends beyond our planet.
MIT researchers are exploring the use of robot insects for space exploration, particularly for missions to Mars. The thin Martian atmosphere poses significant challenges for flying robots.
To overcome this, they are developing robots that jump instead of fly, using a technique called Pogo stick locomotion. Imagine a robot, light as a feather, with powerful legs that can propel it into the air. This is the concept behind Pogo stick locomotion.
By rapidly extending and contracting their legs, these robots can launch themselves into the air, covering significant distances in the low gravity of Mars. This method of locomotion is incredibly energy efficient, crucial for robots operating far from Earth.
These jumping robots could be used to explore areas inaccessible to traditional rovers, collecting valuable data about the Red Planet.
Subscribe, like, and share Cosmo Academia. Section 6. The power of many miniature search and rescue and spybots. One of the most exciting prospects of robot insects lies in their potential for collective intelligence.
Imagine a swarm of these tiny robots, each equipped with sensors and communication devices, working together like a colony of ants. In the aftermath of a disaster, such as an earthquake, these swarms could be deployed to navigate rubble, locate survivors, and relay vital information to rescue teams. Their small size would allow them to access tight spaces unreachable by humans or larger robots, increasing the chances of finding survivors.
The military is also interested in the potential of these robot insects for reconnaissance and surveillance. These spybots could be deployed behind enemy lines, gathering intelligence without being detected. Their small size and ability to fly make them incredibly difficult to detect, giving them a significant tactical advantage.
Section 7. A mighty engine in a tiny package, pen-sized combustion. Powering these tiny robots for extended periods is a significant challenge. Batteries, while improving, still have limitations in terms of energy density.
MIT researchers have made a groundbreaking development, a pen-sized combustion engine that could revolutionize how we power small robots. This miniature engine, a marvel of engineering, runs on a mixture of fuel and air, generating enough power to keep a robot insect aloft for hours.
The engine utilizes a novel design and advanced materials to achieve incredible efficiency and power output for its size. This development could significantly extend the range and operational time of robot insects, opening up a world of possibilities for their use in various fields.
Section 8. The ethical considerations. As with any transformative technology, the development of robot insects raises ethical concerns. The potential for misuse of these tiny machines, particularly for surveillance and espionage, cannot be ignored.
The idea of swarms of undetectable robots raises privacy concerns and the possibility of misuse by governments or individuals. There are also concerns about the environmental impact of these robots. The production and disposal of these machines, particularly if they are not biodegradable, could have unintended consequences for ecosystems.
It is crucial to address these ethical concerns alongside the technological development of robot insects. Open discussions about the ethical implications of this technology are essential.
Regulations and guidelines for the development and deployment of robot insects are necessary to prevent misuse and ensure these advancements benefit humanity.
Section 9. The future of robot insects, a world of possibilities. The world of robot insects is still in its infancy, but the potential is staggering. These tiny machines have the potential to revolutionize fields as diverse as agriculture, healthcare, disaster relief, and even space exploration.
Imagine a future where robot insects help us monitor and protect endangered species, pollinate crops with precision, or even perform minimally invasive surgeries. These possibilities, once confined to the realm of science fiction, are now within reach.
As we continue to push the boundaries of miniaturization and artificial intelligence, the future of robot insects promises to be nothing short of extraordinary. It is our responsibility to ensure that these technological advancements are used responsibly and ethically for the betterment of humanity and our planet.
If you enjoyed this video, don't forget to subscribe, like, and share Cosmo Academia for more fascinating insights into the world of science and technology.